want to welcome everyone at this meeting, and it will be a busy week for us, and it's good to see lots of names. I don't know why the camera is still on David. Can people hear me? Or okay. A few announcements. The main announcement actually is coming from Voros. He this morning emailed us that with sad news that one of the greats in our field, and Sibuya, has passed away in April already. I mean, I don't know how many of you know him, but he has done great work in the theory of differential equations, difference equations. If you go to his titles, you see definitely Javray asymptotics, the calculation of Stokes multipliers being mentioned there. Unfortunately, I never met him, but I've always heard people speak very positive about him. So that's the sad news for today. A little bit maybe of etiquette for this week. It might be hard for some people. Can you please not mention any of the results of the football of today? I mean, that's not an issue now, but at 2 o'clock there's a game starting that some people might have interest in. But let me now hand over to Peter Clarkson, who's the chair for this session today.
Okay, thank you, Audrey. So welcome to this summary workshop. Just remind you that the workshop is being recorded. So if you don't wish to have your appear on the video, then keep your video switched off at all times and use the chat if you want to ask any questions. This morning's speaker, Davide, is happy to take questions as you go along. So if you have a question and you're happy to appear on the camera, unmute yourself and ask the question. Otherwise, can you please keep yourself on mute? And finally, you can switch off the live transcript if you don't want to have that appear on your screen. So without further ado, it's a pleasure to welcome the first speaker today, Davide Masoero from Lisbon, who's going to talk on asymptotics plus functional equations equals exact quantization conditions question.
So thank you very much for the invitation and for the introduction. So here is my talk. Let me put it presentation. Okay, so here is a short outline of my talk. I will first review, make a short review on thermodynamic Bethe ansatz, the ODE-IM correspondence, and a lot of things related to this. And I will use it as a toy model, this very simple cubic oscillator that you see here. And in particular, I will review which rigorous results are known on this more general anharmonic oscillator, which has a monomial potential whose degree is not necessarily an integer number, and also a centrifugal term. And then finally, at the end of the talk, I will briefly speak about my results towards a rigorous proof of these things, which is called ODE-IM correspondence for the Quantum KdV model. So a few caveats before I start. One is my handwriting is terrible, as you can see. So yeah, it's possible that you don't understand everything that I write. The second is that I'm not an expert of the exact WKB method. So I'm speaking of things which are also studied via the exact WKB method, but this is not my tool of analysis. And the third caveat is that since I'm a mathematician, so I try to prove rigorous results. So I'm always dropping behind the theoretical physics literature. In particular, today I will speak of something which appeared in the physicist literature more than 20 years ago, but mathematically speaking, it's still, many things are still unknown. Now, as a general philosophy of these things, which sometimes is known as ODE-IM correspondence, and this thing which is the appearance of Bethe ansatz equation or thermodynamic Bethe ansatz equation in the study of ODEs, It's something that I like to call nonlinear Stokes phenomenon, even though this name is very tentative. So what about the linear Stokes phenomenon? This is something which we know very well, which is the fact that in the neighborhood of an irregular singularity, the asymptotic behavior of the solution of a linear ODE is continuous in open sectors and discontinuous across some lines, which are called either anti-Stokes line or Stokes line. And these jumps and the asymptotic behavior of solutions is encoded in what are known as Stokes multipliers, which are point. So the set of Stokes multiplier of an equation is a point in what is called the space of monodromy data of character variety associated to that equation. Now, what is the nonlinear Stokes phenomenon? Is when you consider a H-bar family of meromorphic connection on P1, which means like just differential equation, linear differential equation, which have the same underlying space of monodromy data. So given this H-bar family of meromorphic connections, you will have an H-bar family of Stokes multipliers. And then you want to study the asymptotics as H-bar goes to 0 of this family of Stokes multiplier. And you will see that the asymptotic is continuous in the open sector of the H-bar plane and undergoes some jumps along some lines. And these jumps are normally described by something which may be understood as automorphisms of the character variety. And this is what I call a nonlinear Stokes phenomenon. Now, I will start with reviewing some early results which are due to André Voros and Sibuya. So in particular, André Voros studied the quartic oscillator and in general the oscillators such that the degree is even. And Sibuya was very interested in the cubic oscillator. Now I will show you today the cubic because for me it's simpler to introduce. So the cubic oscillator, the simplest one you can think of is just this Schrödinger type equation and the complex plane where the potential is a simple monomial of degree 3. And there are you can define a lot of different quantization conditions for this oscillator. Two are very natural. One is called the lateral quantization condition, which is this one with this lateral line, which connect plus I infinity to minus I infinity. And the other one is what is called the central connection problem, which connect the origin to plus infinity. And there is a theory which tells you that there are two entire functions, which are the spectral determinants of these two quantization problems. I will call it today T of E, the spectral determinant of the lateral quantization condition. Okay, and the fact is that this is an entire function of the energy, which vanishes if and only if there exists a solution of the lateral quantization condition. And I call Q plus of E the spectral determinant for the central connection problem, which is an entire function which vanishes if and only if there exists a solution of the central connection problem. Now, it is useful to notice that this function T of E is just the zero Stokes multiplier of this harmonic oscillator as a function of the energy. Now there is something which is very interesting of this function T of E, which is called T system or Y system, depending on the literature. which is the following fact. So first of all, this function has a very peculiar asymptotic at for the energy that goes to infinity. Okay, so we have this. So the logarithm of the Stokes multiplier as a function of the energy has this particular asymptotics. Second fact, which is very highly non-trivial to prove, and it was proved by Dorey-Dunning-Tateo, is that the function T of E vanishes. No, wait, this is not if and only if. So all the zeros of this function T of E are on the negative real axis. And third, which is this, it is this quadratic relation, which is called T-system, is that the Stokes multiplier, as a function of the energy, satisfies this quadratic functional relation, which I call T-system. And this was already studied by Sibuya in the 70s and in the 80s. Now, a very nice fact of this T-system, the same T-system was studied also in theoretical physics by Zamolodchikov at the beginning of the 90s. And he understood that this T-system can be transformed into a nonlinear integral equation, which is called thermodynamic Bethe-Ansatz. So in particular, if you introduce this function, delta of theta, which is the logarithm of the T function evaluated at this point, yeah, minus this is the asymptotics. Then due to the asymptotics that we already know, and to the fact proven by Dorey-Dunning-Tateo that the zeros of the function T appears just on the negative real axis, then we know that this function delta of theta is analytic and bounded on this strip, which is the strip imaginary part of theta less or equal than P over 3. And due to this fact, the T-system is equivalent to this nonlinear integral equation, which is called thermodynamic Bethe-Ansatz equation. And well, it is a very recent result proven by Hilfiker and Runkel a couple of years ago, which appeared in the Annals of Henri Poincaré last year, is that this integral equation admits a unique solution. Okay, and you can actually extend this result of constructing the T-system and then going to the thermodynamic Bethe-Ansatz equation and then prove the uniqueness of the solution of the T.B.A. equation if you consider a more general anharmonic oscillator of this point, which is again a simple anharmonic oscillator with a monomial potential, but now the monomial can have any degree with, if it is, I mean, any integer degree. The difficult point is that if you, so this T.B.A. system, the nonlinear integral equation will become a system of coupled nonlinear integral equations. Despite this fact, the system becomes more complicated with the degree. We have that the results of Hilfiker and Runkel still hold. Now, this fact that Stokes multipliers of linear differential equation, the complex plane, as a function of a parameter satisfy the T.B.A. equation, is a fact that can be hugely generalized. Okay, for example, if you take this other harmonic oscillator, where now the potential is any arbitrary polynomial potential, and you consider the Stokes multiplier as function of h bar. Okay, this is a direct generalization of of the cubic oscillator that I've just discussed. It is direct generalization because you can think in that case the energy is just h bar. Now you can treat this in a similar way, and this as a huge generalization, because it was shown by Gaiotto that this equation are just the conformal limit of a very big construction of T.B.A.-like equation, which describe the hyperkähler metric on the moduli space of a particular supersymmetric gauge theory. Now a remark is that, so this you will get these harmonic oscillators in a particular case when the group is SU2. If you change the group, then and you do the same procedure in the conformal limit, well, will not obtain a Schrödinger equation, but a G open. Okay, which is a direct generalization of the idea of a scalar equation of the second order for a different underlying group. Now, what about the other spectral determinant? The other spectral determinant, which is the spectral determinant of the central connection problem. And then we have a different theory for this. So the asymptotics expansion at infinity is very similar. Okay, so we have again this fact that the logarithm of the spectral determinant is the energy to the power 5/6 plus a small correction. Then we have the fact that the zero of the spectral determinant are real and positive, which is trivial because the problem is self-adjoint. And then we don't have the PT system, but we have what is called the quantum Wronskian functional relation, which is the fact that there exists another associated spectral determinant, which is called Q minus, such that this quadratic relation, which resembles somehow a Wronskian, is satisfied. Now, the beautiful consequence of the quantum Wronskian is that this spectral determinant Q plus satisfy the Bethe ansatz equation, which means that if E is a zero of the spectral determinant, then this ratio of the spectral determinant evaluated at the rotated point in the complex plane takes a fixed value, which is minus e to the I 2 pi over 5. Now, if you introduce what is in physics, it's called the counting function, which is somehow a smooth version of what you would call counting function in complex analysis, then you can prove that this counting function satisfies another nonlinear integral equation, which is called the Vega equation. Okay, I will, well, this kernel is a bit more complicated than the T.B.A. kernel, so I will not write it down here. Now, what is the interpretation of this fact? The interpretation is what is called ODE-IM correspondence. Now, I will briefly review what is the IM, which means integrable model side of this correspondence, which is something called Quantum KdV, which can be thought of as the conformal limit of the XXZ chain. And it was something which was constructed by Bazhanov-Lukyanov-Zamolodchikov in a series of 3 papers in the 90s. The setting is the one of conformality theory. Okay, now we suppose that we have a fixed central charge, C, which for technical reasons must be less than 1, and the highest weight, delta. And one consider define VC delta to be the Verma module of the Virasoro algebra with the central charge and highest weight. Now they were able to define two operator valued functions, which are these strange Q plus and minus of E, and the common eigenbasis of these operator valued functions, which I name V of n, which are the beta states, which are such that the corresponding eigenvalues, so if you evaluate the operator valued function on a state, you will get an entire function. So you got two entire functions, one for the operator Q plus and the other for the operator Q minus. And these two entire functions satisfy the quantum Wronskian and also the asymptotics. Okay, so from this algebraic construction, you will have an infinite number of solutions of the Bethe-Ansatz equation with the same asymptotics. Okay, now mathematically speaking, this construction has still a lot of gaps, and nobody actually was able to prove or interested in proving that all these series which are defined by Bazhanov-Lukyanov-Zamolodchikov actually converge, and that they converge, and the asymptotics is the one that they claim that it is. But I mean, it is a very solid result, which mathematically speaking has still a lot of gaps. Okay, and now we have a conjecture. So we have, so coming back. So here we have like, we started with the spectral determinant of the cubic oscillator, and we find a solution of the Bethe-Ansatz equation of the quantum KdV model. Okay, now we know that the quantum KdV model has an infinite number. The quantum KdV model carries an infinite number of solutions of the Bethe-Ansatz equation. And so the idea is that to every solution, to every solution of the Bethe-Ansatz equation that comes from the quantum KdV model, which means to every state of the quantum KdV model, we should be able to associate a potential such that the spectral determinant of the potential coincide with the solution of the Bethe-Ansatz equation associated to the state. So now we have to fix. So we parameterize the central charge and the momentum, and the highest weight via two other parameters, which we call alpha and L, and the conjecture, which is due to Dorey-Dunning-Tateo and Bazhanov-Lukyanov-Zamolodchikov, can be stated as follows. For every beta states of the quantum KdV model, there exists a unique monic polynomial P such that the solution of the Bethe-Ansatz equation associated to the given state coincides with the spectral determinant of this anharmonic oscillator, which is built as follows. So it has a monomial potential of degree 2 alpha. It has a centrifugal term with angular momentum L, and then it has an additional term which is minus twice the second logarithmic derivative of the polynomial evaluated at this at x to the 2 alpha plus 2. Now it must be noticed that the polynomial P cannot be arbitrary, because we have a discrete set, infinite but discrete set of solutions of the Bethe-Ansatz equation. So this polynomial P must be such that the monodromy about all these additional poles must be trivial. And this condition of the triviality is actually equivalent to a system of algebraic equation for the roots of this polynomial P. Okay, so we could say that this strange system of algebraic relation, which we call BLZ system, somehow should be able to characterize all the solution of the Bethe-Ansatz equation of the quantum KdV model. Now, in particular, if we consider the solution of the ground state of the model, this should correspond to the constant polynomial, okay, which is the polynomial such that this additional term actually vanishes. Now, a couple of remarks. So if you consider the case where you just take the monomial potential with even integer degree, so without angular momentum, without additional singularity, and of even integer degree. Now, this D.D.V equation that I show you for the cubic oscillator already appeared in this guise in a work by André Voros in 1997, which is called exact anharmonic quantization condition in one dimension. I mean, if you look directly at the integral equation, you will not recognize it. But I mean, it's just the same in another space. And the important fact is that in that form, that D.D.V equation was shown to have a unique solution by Arthur Avila in another paper, which is called Convergence of an Exact Quantization Scheme. Arthur Avila, by the way, is a Fields medalist. And this paper is important because even though it treats just a very specific case, it is the only rigorous results about this D.D.V equation that I'm aware of. And with this work by Avila, we know that let's say Bethe-Ansatz equation for the ground state of quantum KdV model as a unique solution, which is something important, mathematically speaking. Now, generalization. This other approach of considering the Q system, the quantum Wronskian, allows for a completely different generalization. Okay, in fact, the quantum KdV model may be understood as a particular case, the case associated to the affinization of the SL2 Lie algebra. So it's a particular case of the quantization of a Drinfeld-Sokolov hierarchy associated to any untwisted affinization of a simple Lie algebra G. Now, in 2011, Boris Feigin and Feigin-Frenkel conjectured that the ODE corresponding to this generalized quantum KdV model should be affine opers with value in the Lagrange dual of the algebra G1. So you start from an affine algebra G1, an untwisted affine algebra G1, and you construct this quantization of the Drinfeld-Sokolov hierarchy. And if you want to construct the ODIM correspondence for this quantum KdV model, now we have to consider opers with value in this Lagrange dual affine Lie algebra. Now, for example, if you consider, well, no, this is a mistake. So if you take AN1, so the untwisted affinization of AN1, so this is self-dual, but again, this is a mistake. If you consider the Lagrange dual of the untwisted affinization of G2, then its Lagrange dual, for example, is the twisted D4-3 algebra. Now, working on this Feigin-Frenkel conjecture together with my collaborators Andrea-Raimondo and Daniele Valeri. And we published a series of papers where we studied these affine operas, and we were able to associate Q functions as generalized monodromy data for these affine operas. We proved that the higher rank analog of the quantum Brownian for these operas hold, and we call it QQ system, which was a name already introduced in the quantum integrability literature. And finally, we proved that these Q functions that we have defined satisfy the Bethe-Ansatz equation associated to the Quantum KdV model. And afterwards, building on our work, Feigin-Frenkel and Davide Hernandez, they also provided a construction of the same QQ system on the EIM side of the correspondence. Okay, in the theory, in the representation theory of a quantum group. Okay, but now going back to the SL21 case. So now we have this conjecture, which is the ODE-IM correspondence, which I tried to picture in this slide, which is a conjecture among a quantum model and a set of differential operators, and mediated by the Bethe-Ansatz equation. Now, to be more precise, we consider the states of the Verma module of a fixed level n. Okay, the level more or less is the number of particles, and we know it's very simple it's a very simple fact that if you restrict to a given level, big N, then the set of states is finite, and its cardinality is exactly the partition number of big N. So on the other side of the conjectural correspondence, we have what are called monster potentials, which are these potentials that I've shown you before, which is a monomial plus a centrifugal term plus this strange second logarithmic derivative of a polynomial of degree n, big N, whose roots satisfy the BLZ system. Now, in order to, so we don't have any direct relation between these two set of objects, but we have an indirect relation, which is the Bethe-Ansatz equation, which is the fact that we have two arrows, which is very solid, which goes from the monster potential to the solution of the Bethe-Ansatz equation with this particular asymptotics, which is just, the arrow is just realized by considering the spectral determinant Q+. And then we have the other arrow from the Quantum KdV model to the solution of the Bethe-Ansatz equation, which is still solid, but mathematically speaking, a bit shaky. In order to prove this ODE-IM correspondence, we would like to be able to reverse these arrows, okay? Because if you are able to reverse the arrows, then we will have a proof of the ODE-IM correspondence. Now, in this picture, so this big N number at the level of the Bethe-Ansatz equation is missing, and I will introduce it in the next slide, together with a theorem, or enormous theorem by myself and Riccardo Conti, that appeared in JEP last February. It is almost a theorem because there are a few technical details which we were not able to prove. And it's about the monster potential, and it says that if the momentum L is large enough, there exists exactly partition of n monster potential of degree n. And if you fix a partition nu of big N, there exists a unique monster potential such that the low-lying roots of the spectral determinant Q, which means the bottom of the spectrum, satisfy these asymptotics. Now, there is like a dominant term of the asymptotic, which does not depend on anything. And then the subdominant term is kind of it looks like the spectrum of a harmonic oscillator, but where you don't take all the possible states. Okay, there are some holes in the states. And to be more precise, I mean, there is a picture here. So if you consider, for example, the empty partition of the number n is equal to 0, then the roots will be all the non-negative integer numbers, just like in the harmonic oscillator. Now, for example, if you take the partition 1 of the number 1, then you have to insert a null at the ground state of the harmonic oscillator, and instead putting a root at the level -1, etc. So there is in this large momentum limit, the spectrum of the Wronskian, I mean the monster potential looks like an harmonic oscillator, but with a spectrum that depends on the given partition. Okay, and so this is the number big N, which was missing in the picture of the Bethe-Ansatz equation. So to every solution of the Bethe-Ansatz equation, you can associate roots and holes, and you can read from the combination of roots and holes a number big N, an integer number. So the next step of our proof, of our road to the proof of the ODM correspondence, which is still a work in progress, and I think we will be able to put it online in July or September, is the following fact. So as I told you, there are roots and holes of the Bethe-Ansatz equation, and for every system of roots and holes, one can write a D.D.V integral equation. Okay, and the goal is to prove that for every given configuration, the D.D.V equation admits a unique solution of the Bethe-Ansatz equation when the momentum L is large enough. And so far, we have already able we have early results, which are the fact that we are able to prove that there exists a unique solution of this D.D.V equation, which has the same these asymptotics here. Okay, but we want to make this result more global, and so without assuming that these large L asymptotics hold. Now, some concluding remarks. Now, we started from a simple harmonic oscillator, let's say. Harmonic oscillator with monomial potential of integer degree, an object which was studied by, for example, Sibuya and Voros and Dorey-Dunning-Tateo. And we have defined two different paths for the integrability, let's say, of this potential. One is to considering the Stokes multiplier of the potential, and notice that they satisfy the thermodynamic Bethe-Ansatz equation. And these constructions allow for a very big generalization. Okay. And there is a lot of geometry behind this generalization. And then we can take another path, which is, we consider the other spectral determinant for the central connection. And we notice that it satisfies the Bethe-Ansatz equation. And then we can generalize this fact to another class of ODE-IM correspondences, which is like the correspondence between G1 quantum KdV models and OPERs with value in the Lagrange dual of this algebra G1. And these two generalizations, they have for sure something, I mean, an non-void intersection. But contrary to some claim in the literature, I don't think that this more geometrical approach actually is a true generalization of this other more algebraic approach, simply because this monster potential never appeared in this geometrical generalization. And so what I would like to know, to understand, apart from making rigorous this G1 quantum KdV correspondence, or the EM correspondence, is that whether there exists a unifying bigger theory which explain all these different phenomena. And this theory, which I don't know whether it exists or will ever exist, is something which I tentatively call nonlinear Stokes phenomenon. And yes, as I've just told, a global unifying approach is missing, and mathematically, despite a lot of recent advances, now I speak just about the ODM correspondence for the quantum KdV model. Despite recent advances on this direct problem, which is the problem of attaching to OPERs or to a conformal field theory solution of the Bethe-Ansatz equation, there are still very few results on the well-posedness of the inverse problem, which will be the well-posedness of the D.D.V equation or the T.B.A equation of the nonlinear Riemann-Hilbert problem, which are different name for the same fact, which is the fact of being able or not to invert the nonlinear functional relation. Okay. I think my talk is finished. Thank you very much.
Thank you, Davide. Are there any questions?
Davide, just by curiosity, I don't know, maybe the question is just stupid or meaningless. Is there any relation between this quantum Wronskians and what they call Verlinde algebra of loop operators in CFT?
Well, I don't know. I really don't know. No, I'm not the right person to answer this question. Maybe someone else more in the. No, I don't know what is Verlinde algebra.
Are there any other questions? If not, it just remains to thank Davide for his talk. Thank you. And the next talk is at 1:30 p.m. British summertime by tomorrow, Grava. So until then, we'll have a break.